All right, good morning. This is Team Two's fourth progress report of the third on module feeder and plastic detection system. This report will be going over the implementation and risk analysis of our system. I'm Reed Machek, and I'm joined by Wayne Johnson, Caleb Yarbrough, and Daniel Brown. And at this time, I will hand it over to Caleb to get us started.
Good morning. I wanted to start this presentation by doing a kind of a little progress to date overview. At the last meeting, we delivered a recommended solution in order to receive some valuable input and feedback from the client and the faculty. And we took that and applied it to our solution to kind of get it ready for our implementation plan. We finalized our mounting solution with the brackets from the report from Dr. Holt, kind of work out the kinks in that, and also our lens protection, how we wanted to mount that and finalize those two aspects. And in the following slides, we're going to go over our actual implementation plan that the team has developed together. So kind of a systems overview of the implementation. It's not going to be an extremely complex process. A lot of it's going to be just hands-on labor from the gym crew. There's not going to be any serious demolition work since there's no prior system. It's mainly going to be involved like cutting holes in the module feeder, mounting the system and the components, and then connecting that to the software package at the monitoring station. We believe the most time-intensive process is going to be connecting the system to the software package and troubleshooting any kinks or quirks that may arise, as it always does with technology. This software package was developed by Dr. Holt and some research they did in 2020 about the same type of problem. And then the solution will be installed and connected all at once, since there's no prior system that has to be removed, and it's a relatively short process. And due to long off season, we feel like the client would have ample time to implement this and test it before gym season kicks off full speed. Excuse me. Just some of the personnel requirements. Like I said, it's not involving the entire gym, specifically the monitoring station and the employees in the module feeder section. The monitoring technician is going to be required to have a working knowledge of that monitoring software package, so he can kind of understand and recognize any problems that arise and make sure that the operation of it is smooth and seamless. The floor level employees are the ones that are going to do a lot of the heavy lifting. They play a very vital role in the success of this system. They're going to have to keep close observations on the components, ensuring proper wire connections, no adverse effects with the cotton flowing through, no problems with the module feeder, and also replacing any damaged components and removing plastic when the monitoring technician tells them that they have plastic on the module feeder rollers. The final point is just communication between the monitoring technician and the floor employees, whether that be through walkie-talkies or some kind of short-range UHF or HF radio. Going to be absolutely vital. If they cannot communicate when there is plastic on the rollers, the system is not going to function and work as it was intended to. So communication will be absolutely vital to its success. I'm going to pass it now to Reed. He's going to go over some more of the implementation.
Yes, thank you, Caleb. I'll be covering our selected implementations for this system. Like we said in the past, the camera lens is just 2.8 millimeters. So we felt that a square piece of Lexan cut at 2 inches squared will provide enough visibility for our camera. A square piece of Lexan we felt like is much easier to cut rather than a circle that would be the same dimension as the lens and it would theoretically do the same job. We decided that the best option for cutting the holes in the feeders to use a plasma cutter or a cutting wheel, because a normal gas torch might cause the walls of the module feeder to warp or be distorted just because of the amount of heat it puts out. We recommend cutting the piece of Lexan an eighth larger all the way around to ensure it covers the hole completely in the module feeder. Toggle clamps will be fastened right above the cutout using 4 3/8-inch bolts. The positioning of the camera bracket is a predecessor for the positioning of the toggle clamps. The toggle clamp will hold the mounting bracket in place when pictures are needed. And then the swiveling bracket housing will also be bolted to the feeder wall so the camera can take pictures or video whenever you desire. Cat5 cables and power cables, at least 50 foot long, we felt would be desirable length to connect the camera to directly to the control panel. We will include step-by-step instructions directly from DHUA and this will just be beneficial in programming and power and troubleshooting the cameras. And our selected light housing implement from GG Lights is only 1 inch and 3/4 inch deep, so we feel as if the lights can be mounted inside of the feeder. The hardware, like bolts and cords, all come with the lights, and a 1 inch hole we felt would be needed to be drilled a 1/2 inch to the right of every light, so the power cord has a direct path to the outlet. We chose to install a rubber grommet within that drilled hole or cutout hole, so the power cord is sealed from the module feeder and free from friction while the feeder is running. And as y'all probably know, and Mr. Green probably know, grommets are pretty cheap, and most of them can be found at any hardware store or gin or Tractor Supply. Okay. And this chart, we've created this Gantt chart to kind of provide gins when they decide to implement this project, which of course the series of subsystems will depend on how long it takes the gin to acquire all the components. We based this chart on if 2 workers were to be assigned to complete the system, so we decided that as all 7 holes in the module feeder were being cut, that the other employee would be assigned a task of cutting the Lexans lens covers. Mounting the lens covers will be the task after the holes are cut out, as is the rubber grommets being placed in the holes when the power cord inlets are cut out. Mounting the swiveling brackets and cameras will take a long period of time, so we decided that both employees should probably tackle this for the majority of that step in the time. The next step in finalizing the system will be programming and troubleshooting, which will also be very tedious, so we felt that all hands on deck should be assigned to that task. All in all, we felt that this process shouldn't take over 6 hours. We feel about 5 to 6 hours, and which seems like a lot, but if the system is completed before harvest season, we feel like it can reduce downtime if you were to implement this right before the season starts. And I'll pass it now back to Caleb.
And just kind of to supplement the Gantt chart that Reed just went over, this is kind of a precedence graph showing the order and the sequence of steps and how the system ties together kind of in a network of starting from the first step going to the last step. And obviously these are in hour increments, so 0.5 hours, 30 minutes, 1 hour, 45 minutes. And this is just kind of like I said, a supplement to the Gantt chart to give the client an idea of how each step will flow once implementation has began. And as we explained in the Gantt chart, the longest part of the process that we estimate is actually running the system to the monitoring station, installing the software package, and making sure it's operational and working properly. And now I'm going to pass it over to Wayne. He's going to go over to the risk analysis.
Morning, my name is Wayne Johnson. I'll be going over a few of the risks that we've gotten from our own research as well as from the client in our last presentation. The 4 that we feel to be most pertinent for this are the possibility of the lights getting too hot and igniting the cotton, the safety risk of employees entering the module feeder to remove plastic, the risk of our final solution being ineffective for solving the problem that's at hand, as well as pausing the feed too long and causing that hopper to run out of cotton, because that's the essential part of the pause, the time that we have to allow the system to take a picture of any potential contamination. First, I'll be going over that heat risk. So this risk is kind of already mitigated just by us recommending LED lights as opposed to other, like an incandescent light. But so to analyze this, I wanted to present exactly how much heat we're going to get in a temperature change. So I use this equation, we learned it in Dr. Costello's course. A few of the necessary figures that were required for us to get some of these data. I'll go over them real quick. So first, it'll be that those lights that we recommended from GG Light use a 7-watt Philips LED chip. So we have 4 light bars. Each of the 4 light bars has 6 of those chips. So we're considering it to be 24 LEDs. We're using an estimation that LED lights are approximately 70% effective. So 70% of the energy that goes into them is converted into light, and 30% is removed as excess heat. Other figures that were necessary for finding out this mass rate are just how much, in our economic analysis, we mocked it up as a gin that was doing 100,000 finished bales at the end of the season. So we back calculated it in reverse to figure out how many modules that'll be and using the weight of each module. We also used that this will be over a 6 to 8 week season as another part of research that we found. So for calculation purposes, we just called it 7 weeks and operated 24/7 during that period. So that gives us 49 days of operation. And also for this specific heat number, this is from research that was conducted back in 2003 to find out the specific heat of each of the components and constituents of cotton. 0.46 calories per gram per degree Celsius at 30 degrees Celsius is just an average of each of those components. So at the end of all that, what we came up with is that this will increase temperature by 32 degrees Fahrenheit inside of the module feeder. That figure is kind of vague or useless if we don't know more about what's the dangerous temperature. So not only is the risk of the cotton being ignited a problem, but also the potential risk of those LED lights burning out just because of how hot the environment is. So those LED chips, according to Phillips, should not exceed and operate at an ambient temperature in an environment of 80 degrees Celsius with a list that converts to 176 degrees Fahrenheit. The auto ignition temperature for oily cotton. I use oily cotton just because it's the lowest auto ignition temperature. Of course, if it's dried or already ginned, those are of course higher. So if we can mitigate it all the way down to the lowest auto ignition temperature, we should be fine. This comes from transportation information system. So it's a database of information about storing and transporting different agricultural commodities. All in all, heat causing the cotton to catch fire or burn out. The lights should not occur so long as the ambient temperature inside of the feeder does not exceed 140 degrees Fahrenheit. So we feel like that we don't know exactly the figure for the ambient temperature, but I feel that 140 degrees is pretty hot. If it's not that hot in there, then we should be fine. Especially since we calculated this with that specific heat at 30 degrees Celsius, which is about 86 degrees Fahrenheit. Next, I'll be going over the employee safety risk. So since we aren't introducing any tasks to the gin crew that aren't already needing to be conducted, as far as reaching in and pulling out that plastic contamination from the feed rolls, we believe that those risks should already be mitigated by adhering to the OSHA and other bodies' regulations. Specifically for OSHA, those would be following the Code of Federal Regulations, Part 1928. That's for just agricultural operations. We mentioned way back in the very first part of this report about cotton dust. So that'll be following CFR 1910, Part 1043, and its subsection A and 2, as well as, of course, the general duty clause for following OSHA regulations. And I'll pass it to Daniel to discuss the other two risks.
Thank you, Wayne. So first risk I'm going over this morning will be the risk of having too much downtime. As we've said in our previous prior reports, there's going to have to be a slight gap in the feeding of the modules in order to take a picture, video, whatever, to get that image to see if there's any of the plastic actually in those spindles. Obviously, this will be necessary to use the camera system at all. How long that gap is will kind of have to be gauged by testing it, but obviously we want to minimize this time taken, because if we take too long to look for plastic, it'll lead to further losses due to the downtime, as I mentioned, and downtime in the gin can lead to poor financial losses. So within the module feeder itself, there's a hopper after the module is torn down that fills up with seed cotton, and over time that level goes down. And as long as we keep some cotton within that hopper, then this will not be a problem at all. The main mitigation to this risk will be to minimize the time that we take to take that image. And then to give you all kind of an example, this isn't necessarily the module feeder that we're working with, but this one is one from Lomas, and the hopper, if you could do the mouse kind of in that corner.
So down here,
Yeah, kind of in that bottom corner there, that's where the hopper actually is. That's where the cotton gets fed into to go into the rest of the ginning system once it's broken down. And then the other main risk that we came up with was obviously just the solution not being effective as we would intend it to be. If it ultimately is not effective, the gym will be out approximately $1,000 for all the supplies that go into building the system. On top of that, the losses that they're already going to have from the plastic contamination. The main mitigation to this risk is conducting thorough research to ensure that it will be effective in the end. And then I'll be passing it over to Reed to finish off.
Yes, thank you, Daniel. Next, we'll finalize the details of our solution and aim to meet with Dr. Harden to figure out the rest of our presentation for our final presentation. So at this time, we will be open to questions. Thank you.
All right, thanks, fellas. Y'all can stand up there kind of in the camera if you want to, and we'll ask Team 1 to make your questions and comments.
Yeah, well, first off, I thought y'all did a really good job with the hybrid presentation style. It didn't seem to hinder y'all's ability to effectively communicate at all. So good job with that. But I always like y'all's slides. They're always concise, straight to the point, but they're always full of information. And everyone just always seems to be really educated about what y'all are talking about and just having knowledge on hand. So good job overall.
Appreciate it.
Yeah, I really liked how y'all utilize tools that we've learned, Ag Systems, the Gantt chart, and critical path analysis. I did have a question. So when y'all mentioned installing these cameras, Reed mentioned using plasma cutter. Is that a normal piece of equipment that cotton gins will already have?
No, that's what we've kind of discussed. If they have a plasma cutter, that would be ideal, but that's kind of why I put the grinding disc. Figured most gins have a grinding or cutting wheel or Dremel. You can knock a 2-inch by 2-inch hole out pretty quick.
I thought y'all did a good job transitioning between people. Y'all seemed very prepared, and y'all did a pretty good job.
Thank you. All right, thank you, Team 1. I appreciate y'all coming right out with 4 questions and comments. Good job. All right, Mr. Green, over to you.
All right. So I guess well, let me ask this. What are the grommets for? I understand the cord's going through the metal, but what metal is the cord going through?
It'll be going through the side of the module feeder wall. The light will be mounted to the inside of the wall.
Oh, it's for the light. Okay, so the light is inside the wall.
Yes, sir.
And the camera is kind of outside the wall, looking through a piece of glass.
Yes, it's
Yes,
full.
And I guess I'm not sure where are the lights? That one thing I was struggling with in the presentation was trying to figure out where these lights are going to be. I get inside the wall, but inside the wall where?
They'll be positioned right next to the cameras, kind of on the more entry side of it, so that they're not blocking the camera, but so that they can still provide light so that you can see them.
Down low or up high?
Up high, angled downward.
Okay, so y'all are going to shoot from the top and look down and try to get the bottom few cylinders.
Yes.
Okay. I like the whole discussion about the temperature. That was really interesting, and it's a darn good set of thoughts. One thing that occurred to me. So you guys are going to pause. You're planning on pausing the system and then taking a shot of it, right? Is that
Yes, sir.
Have you thought about the relay that pauses the system? Could it turn on the light so your light's not on all the time?
We hadn't considered that,
but it very well could,
Yeah.
being wired into the PLC that the software is already manipulating. So that is a
kill
very
two birds with one stone.
To get
absolutely,
rid of the heat risk pretty
Yeah.
much completely.
absolutely.
Yeah, it just sort of popped into my head that maybe that would, you know, be a good combination. So go back to that little chart with the circles and the lines. And of course, you guys are all like in the same class and taking the same classes, so I suspect this makes sense to all you guys, and you might assume that anybody with a brain could understand it, and that could be the problem. But tell me, I have really not much of an idea of I mean, I kind of know what this is, but not really. Like, there's different colored lines,
You want me to go back to the chart first?
and
Yeah.
well,
So it supplements the Gantt chart, kind of laying out the order of which steps will occur in the process and kind of the precedence. And what it seeks to find is what's called the critical path. That is the longest sequence of time the steps in the process will take to complete the project. So based off of the information and the order and time estimates that we've given for each step in the Gantt chart, I constructed the this graph in QM, which is for project management software, and it gives each step a time value, and these red lines, and of course in this scenario, multiple critical paths are detected. So given our estimates, a lot of them are half-hour increments just because we feel like that's a realistic time estimate. That's why there are multiple critical paths, and that's what the red line indicates. And it gives kind of a network view of how each step ties into the one before it and the one after it, heading towards that end state. Does that answer the question?
I think so. So like from I to J, the 2 over J tells you that there's 2 additional hours from I to J.
Yes, sir. Correct.
Okay, yep.
That step in the process will take 2 hours.
Okay. Well, I like the way you guys are heading, and I like the way you guys are communicating. I'll tell you, you as a group have done a better job as a class, the whole group, than any we've seen in a long time. So I appreciate the way you guys are working on this.
Thank you, sir.
Thank you.
Y'all can have a seat. So Wayne, I'll probably need you to stay up here and change the slides for me. Okay, yeah, good presentation, about 15 minutes long. While we're on this slide, I'll talk about it in a minute. Risk analysis. Risk analysis. That was what we're looking for risk analysis, okay? Your risks were associated with what happens when we implement the solution, what bad things can happen, and what are we doing to mitigate those risks. You had at least 4, and one of them addressed 2 risks. Your the heat with regard to the LED lights. You even referenced Dr. Castell's class. So wow, I'll let you comment on the content, but nicely done on the risk analysis. I wish I could just stand here and talk about all the good things I liked about the risk analysis, but it was that was exactly right. I feel like the implementation plan is a little bit off though, and I'll tell you why. Let me start by asking this question. What is the difference between an implementation plan and installation? Anybody?
I would say installation is just mounting different components, and implementation is tying it into the normal operations of the gen and realizing what effects it's going to have on normal operations.
Okay. So what you guys did, and you know what, you went through the details of it, and I like it. So I'm not going to ding you too much here, but you guys really went into the details of how to install the solution. And so that's what this is. What's missing off of this chart? I mean, great effort here, okay? This is from my class, from Ag Systems 301. But what is A?
labeling the activity.
labels explaining what each.
I mean, you guys know,
Yes.
but actually, I bet you don't have it memorized. Daniel, what is E? Couldn't tell you from that slide. Now, so you're thinking, okay, well, I'll just flip back to the next slide. Go ahead and do that. The problem is they're not labeled either. I think this is probably A, B, C, D, E, et cetera, right?
Yes, sir.
But it's not there. And so your client was confused, and but hey, good effort. But I would say your Gantt chart here. All right, ultimately, it's going to take one work day.
Yes, sir.
That's really all your client needs to know. I mean, your step-by-step instructions will cover the installation of this. Although, Reed, you
Yes, sir.
said you promised your client that we will include step-by-step instructions. Are you really going to do that? Are you going to provide your client step-by-step instructions?
Yes, sir.
Okay. That'll have to be an appendix to the report because it's going to take a lot of pages. I don't want to have to grade that. Okay, that needs to be an appendix. Okay.
Yes, sir. It's a link straight from DAHUA.
It's from the camera for the cameras.
For the cameras.
Getting those set up.
Okay, not the installation.
No, sir.
No, not the
Okay,
whole thing.
so it was a little bit of misunderstanding there. So I appreciate the Gantt chart. It's that's good, but probably what you need, what we're looking for in an implementation plan, is the implementation of it. So one would be installation. Another step would be perhaps training. Another step would be testing, and then the fourth step would be the actual, what's going to happen when plastic is detected. And so that's hard to timeline that out. So what you've done is you've got a really good Gantt chart of the installation, and that's good. I'll give you points for that. But ultimately, that's not what we want to talk about the implementation of the plan, not just the installation of it, okay? So, but that's okay. Probably the biggest critique I've got is go back to your selected implementation slides. Yeah, right here is a list of components. What did I write down here? So you've got a list of components, and Reed, talked about how he's going to install all these, but really, a drawing or some kind of flow chart or something about how they go together would have helped here. So a diagram or a drawing, and I realize that's going to be tough to do, but this just really wasn't helping me very much. And the last thing I'll talk about is, Caleb, one of your slides. Go back to the slide about personnel requirements. Okay, I like this, but I have some questions about it. So it looks like we have a monitoring technician and floor level employees, plural. How many?
Two. Yes, sir.
So we're missing some numbers. So I'm seeing, I figured there's at least 3. And my question is, are these new employees or are these existing employees who are going to have additional responsibilities?
Existing employees that are going to have additional responsibilities. The employees that are already in the module feeder section of the facility.
Okay, so there's going to be some training that goes on here with these guys.
Yes, sir.
All right. But hey, nice presentation. Your risk analysis was eye-wateringly detailed, and but in your implementation plan, you got the right. Your bullets hit a target, but it probably was a little too focused and didn't talk about the entire solution. So good job, Dr. Castel.
Yeah, I agree. Excellent presentation, excellent delivery, good contact. I like the Gantt chart. I was totally confused by the critical path analysis because I don't know that. So Professor McGee made exactly the right comments. Label it, tell us what you did, because it happens to us when you are teaching. We know the topic, we assume you do, and we realize that we have to do a better job. But it was a very good way to describe what we take and how long. So I like that. I appreciated that you use material from my class. Can you take me back to that slide? I just have quick comment.
Grade their homework, yeah.
You know, when I look at the units, you're mixing units, so I'm assuming that
In the calculation,
Okay, yeah.
they're correct. It's just, since I referenced
you're
it,
just showing me
Okay.
the stuff. Yeah, just make sure that you're using the right units. But I think it was a great way to quantify if you were in the danger of burning up that material that, you know, even though it will change temperature very quickly. So I like to see that you're using other classes, and especially 315, which is always hard. So I was, Daniel, you could talk about the risk of how long will it take? So it makes me question, do you have an estimated time? I think you said that it's hard to tell unless you do research to how long will it take to take a picture, but do you have any idea?
I'm thinking probably less than a minute, but it's
Okay.
hard to estimate based on, you know.
But yeah, I understand that. But you're talking about that, like, is that a lot? Because you keep saying the risk of taking too much time to take the pictures. So what would be a lot? What would be too long? I had a question. What
I guess I don't really have a quantifiable number, but just any period that's long enough for that hopper, like I said, to run out of cotton. I'm not exactly sure how long.
There's
that
no
would be
way
for
to
sure.
tell unless you actually. Okay.
I should have asked the client about that, and
Yes.
that's on me, but
Yeah, they might know. They
from
might
what
have
I tried to find just online, I couldn't find an exact number of how long that would take.
That's good. That's good. Okay. So anyway, excellent job. I like your slides. Very concise, very little text, and you explain very well. So good job.
Thank you. I have one question since you are here. So this slide, you're telling me if I like have a 50 watts heat resource and then I can heat almost 2,000 pounds per minute of air stuff for 32 degree Fahrenheit. Is that what you're implying?
so what it is, so we tried to find, the mass is a kilogram per second.
Right.
The reason why, when I was calculating, I felt a kilogram of flow rate like that was necessary is because, so those 7 watts, comes from Phillips for the lights. A watt is a joule per second.
Right.
So when you divide these figures over these to find that missing temperature, it's going to be joule per second over a mass flow per second.
Right.
So there is quite possible that this is not correct as far as, this is what the best estimation we can come up with for how much cotton might be flowing through the system at a given time, just because it was necessary in order to, because
Right.
you need a mass to run this equation.
Right, I understand. But after you run the calculation, you have almost 50 watts of LED. Let's assume it's a heat source, and it can heat up 2,000 pounds of per minute of cotton by 32 degrees Fahrenheit. Do you think like that's kind of reasonable in your calculation?
When I first saw 32 degrees, with each of us, when we did this over a Zoom call, it seemed kind of high. But so that's why we went and got the figures for how at what temperature would the cotton ignite. Mm-hmm. So in relation to, in a vacuum, 32 degrees seems a lot of extra temperature, a lot of extra heat. But compared to how hot it would have to get to ignite, we feel it might be reasonable for an estimate.
Sort of a worst case scenario.
Okay.
Yeah.
So also the electric friction,
Right,
many on there.
Yeah, I was just like thinking about 50 watts will do all this work, and that was a byproduct. Just
Yeah, I think the client would have been happy with you know, the cotton flowing through the module feeder is just there briefly, so it's not really going to reside there long enough to have a significant temperature change. And the temperatures in the module feeder are really ambient temperatures. The hottest place you're going to find in the gin is going to be the dryer. As it's drying the cotton, it's going to raise the temperature to something that is knowable. I think maybe 150 degrees. But really nowhere in the cotton gin are you going to have a problem with the LED lights causing the cotton to catch on fire because of the rapidly moving cotton, unless it gets caught there. And so what I like about this slide is you identified a risk, and you knew we would ask questions like, well, how hot does it get? And so you attempted to answer that. Even though it's an overestimation, you made an attempt at it. So this is really, I appreciate that. It's probably, yeah, overkill, but that's all right. Kelly, are you concerned about the LED lights catching the cotton on fire in the module feeder?
Always. The thing that you worry about, you hit on it there, is buildup. Things tend to pile up on things that are inside the machinery if they're not perfectly smooth. So yes, when I hear lights inside a machine, I automatically assume that things are going to build up all around the lights, and that is a concern.
Yeah, overall, what this project needs is a little bit more detail in where these lights and cameras are actually going to be installed. I'm still grading your papers on the recommended solution, but your diagram is simply a side view of the module feeder. You need a top view with some dimensions, how far apart these lights are, that kind of stuff. You know, don't get too down in the weeds, but the client needs to know something about how many cameras and lights and about how far apart they are and all that. And the problem is, obviously, different gens are going to have different size module feeders. So you need to give something that'll be useful to different gens.